Welcome to Lesson 5, Thermochemistry. Are you ready to do a little bit of lab work? In this particular chapter, you will be looking for the heat of combustion for a candle. And we're going to be getting pretty mathy. Expect to see and work out problems and work them out more than once. I sometimes think of this chapter as our first really advanced chapter. Sometimes students find this to be a little more challenging, so email me anytime you have questions. When we're looking at this candle and we're thinking about the energy flow, like we did a little bit last chapter, you want to remember that the molecules are what's making things happen. Molecules are moving. So this candle feels hot because the wax is participating in a combustion reaction, as we talked about before, which is exothermic. Energy is being released. Even just holding an ice cube in your hand will give us a change in energy, which is thermochemistry. So phase changes are more of a physical chemistry, a physical change. Burning a candle is a chemical change. But for any particular substance, if you're looking at its phase changes, you could do this for wax as well. But this is figure 1712 in your book, and if this heating curve makes sense to you, you can actually use this to do all of your problems. Once again, we are looking at heat added, which is an endothermic process if we read from left to right. If we read this x-axis from right to left, it's an exothermic reaction. We're going down the stair steps because heat is being removed. And temperature is just average energy in the particles, and total energy in the particles is heat. So if we're looking at water, and we're starting at below zero at the very beginning, and we're going to start adding heat, you can see that our line goes up. So as long as we have ice somewhere below 0 degrees Celsius, as we add energy, it stays ice. But when we hit 0, the ice melts. Temperature will not change during melting ice. It's a simple lab you can do. Just put a thermometer in a little cup of ice water, and you're going to see the temperature stays very close to 0, maybe up or down a little because of fluctuations in convection currents in your water. But it's not going to start getting to room temperature until all the ice is gone. And so as your liquid heats up, we start going up on our stair steps. And then what happens at 100 degrees? The water's going to start boiling, right? So we call that vaporizing. And then we can even take all of that gas, and then we can start heating the gas. It's possible to actually burn paper with gas if you just keep heating the gas. I think you can probably find that on a YouTube video. But notice we've got these 3 equations. Delta H equals MC delta T. Delta H equals MC delta T. Delta H equals MC delta T. Okay? MC delta T. Whenever you have a temperature change, is delta T. Triangle means delta. Greek letter delta means change in science, chemistry, and physics. So as long as you're going up the curve, your temperature is changing, use MC delta T. But then on your 2 flat places, notice we have a different equation, the white equation. Change in heat while you're melting something is the mass that you're melting times heat of fusion, which you look up. When you're vaporizing, mass times heat of vaporization will give you the change in heat for the substance you're vaporizing. Noticing that you can also go down, right? So if we have a gas, we can cool it down. At 100 degrees, water gas will turn into water liquid. And then once all the gas is turned into liquid, we can cool it down some more. And as we cool the liquid, then it will freeze. Notice that melting and freezing are the exact same amount of energy. So the only thing you do here, if you're finding the heat of crystallization or the heat for freezing, you just change the sign to negative. All right? Losing energy is negative. Exothermic, losing energy is negative. Gaining energy, going up. Endothermic, adding energy, plus, positive. All right, I hope that's helpful. One last thing. I've got a birthday candle. All right, it's just a small candle. I'm just going to heat the bottom of it a little bit. And then I'm going to stick it on a plastic cup straight up and down. And then I'm going to light this one too. I like thermochemistry. There's plenty of excuses to have fire with a supervising, responsible adult. And then I'm going to light this birthday candle. And what am I doing? I'm burning, right? What am I burning? The wick, yes. But what else am I burning? The wax, right? If you get the opportunity, and we don't have time, so I'm not going to show you the whole thing, but birthday candles are small because all they need is the wax to burn. It's not trying to make it last very long, so there's no wax to come in and pool in and to burn longer like this tea light. But we are combusting the wax. It's turning into carbon dioxide because it's a chemical change. Where will the wax be when the candle is completely done burning? Let it burn. Make sure it's perfectly straight up and down. And see. You might stop now, but I'm going to tell you the answer, so if you don't want to know the answer, this is it. But the answer is, all the wax is going to turn into carbon dioxide. You're going to be left with almost no wax at all. Complete chemical change when burning. Your candle's not melting. It's not going to be wax anymore. It's not a phase change. Burning is a chemical change. Just like going back to our bodies, we eat our food to get the energy. It's not food anymore. All right, take your time. Do your math problems carefully. Don't be afraid to do a math problem, mess it up. Try again the same problem until you get it right. That's okay. And there's a lot of help out there on the internet too if you prefer watching videos. And my favorite, just email me. I love hearing from you. Bye-bye.